make sure you have the same rows selected as shown here, as well as the label, the level, not label.
Does the level matter for the rejected ones?
Yeah. So make sure you have both fiber and sugar as input here. And later I'll show you how to reject one of them during one of the later nodes, that you don't have to reject them before front, or you don't have to need two data sources in order to, use different sets of variables. Are you good? We move on? 1 second, okay. It's converting the data set takes some time. Can you not see clearly? Do you need a magnify? Do you need enlarged if it helps? No, yeah. That helps?
Yes.
Great. Well, just so you know, this is recorded, so you don't have to think about too much about future. Future is taken care of. It's only now. Okay? Everybody's good? Great. So at the end of the day, you will have 2 input, 1 ID, and 1 target. The ID is not super critical, but it's better to have one if you have. Okay. Now. Good. All right. Move on. Confirm that you have 77 rows. Okay, we need a new diagram. Okay. So the project is prepared. Now the first thing, as always, would be to explore the data set, to look at the missing values. And the first thing I need to change is for it to also include the interval variables. And because I know this data set, there is some missing value in it, but other than that, there is not much unexpected. So I will continue to add another node. So in this case, typically, so regression is still a supervised learning method, and to make a good prediction model, you need cross-validation, right? For the homework, to get the same results, to get the results that are expected, I hope you keep everything in the same sample. So then you will not need data partition just for the homework, but otherwise, for project-wise, you need it, right? So I don't need to use a data partition, and because I know there's a missing value here, so I will need an imputation node that would be modified. And if you are familiar with your data set, supposedly, that you have done exploratory analysis, you have understood the missing value situations, you have a pretty good understanding about the variables and what variables have missing values, and other peripheral information about those cases that have missing values, then you can use a default method for you to automatically impute missing values depending on the type of variable. Here, the class variable property setting will not make an impact because we don't have any nominal variables here. Only the interval variable method will make a difference. And as I emphasized, interval variables may have skewed distributions, and compared to mean, median would be almost always a preferred method to impute the missing values. So I would do you would do median, and by this point, I think you can run it so that it runs all 3 nodes. So examine the results of impute. Make sure something is that missing values are taken care of. Sugar, 7 missing values have been modified. What now? 7 is the replacement. So 7 is the median for sugar, I think. Number of missing cases in training is 1. And there's only one set of data, which is the training set. And to go back retrospectively to look at the results of the stat explore. There are 2 interval input variables. There are no class variables here. there is one missing value in sugars originally. The median value is 7, so the replacement value is actually the median. If you take a look at the correlation of the two input variables with the target, you see that they are fairly correlated. The less correlated one is fiber. Correlation is 0.58. The more strongly correlated is the sugar one, and the correlation is negative, which is, reasonable. Nowadays we hate sugar. Sugar is the evil.
That's the correlation between that variable
with the target.
rating, right?
With the target, yeah, with the rating. And for regression modeling, there is an optional data transformation step that you may or may not do, or you may use to your advantage to diversify your model in hope of searching for a better predictive model. So the reason why you would use log transformation, log transformation is to fix the skewness of the distribution. As with other alternatives, you can do square root as well, or reversed square root as well, as the textbook talked about. But log transformation is a more commonly used technique, and it fixes most of the problem, if not all of them. So it's adequate if you use it. The reason why you need it sometimes is because it lessens the impact that outliers may have on the model. If you have a long tail in some of the input values, then log transformation may help you increase the model performance. But it's not always the case. And sometimes your target variable may also have skewed distributions, and that complicates things. So the bottom line is that there's no absolutely right way to make a judgment. You need to think about what really may help you capture the underlying trend. Does the variables at their original scale will help you capture the linear relationship between the input and the target? Do you believe that the relationship between target and input on their original scale should be linear, relatively linear? When the input is very large, which is in the tail, which is an outlier, do you think that it exerts a similar linear effect on the target? If that's the case, then you may be better off not log transforming the variables. But if it's not the case, then you may be better off to use log transformation. A simple example to illustrate both cases is that, let's say, if you're modeling bidding price of a buyer on a property, and you are using the income as the input. So another way of saying the model is that you're using income as an input to predict asking price, not asking price, bidding price, or your offer price, right? Then you would expect that the higher the income, the higher the price that the buyer is willing to offer. And the relationship might be very linear on their original scale. So you might be better off not taking the log. Taking the log will remove the specialty of this case, which is the high income affluent populations. So which may adversely impact your model performance. But say another case where you're predicting grades with socioeconomic status,
like, household income, parents' education, things like that, then there is a non-trivial segment of the population, maybe 15% of the population, who have higher income than normal. Their family income are in the outliers, but the grades are typically, quite symmetric and well behaved and normal. So you have a natural ceiling for the grade. You can be as good as 4. You cannot exceed 4.0, right? So in that case, the income as being, family income as being an outlier doesn't contribute too much linearly to the grades. The grades have a ceiling effect. You cannot exceed that, right? Because grades are something that is more arbitrary than other things. So in that case, you may wish to sort of to contain the impact, the excessive impact of income outlier effect on the grades. So these two cases are quite different on the target, but similar on the input side. So you can make different decisions and rationalize. But in the end of the day, hopefully you will look at both, and to see which model, a model that doesn't use log transformation, the other uses. You can compare them by using cross-validation, right? And select the model that predicts well. Does that make sense? Yeah. So here I'm just going to demonstrate how to do log transformation, and we'll interpret the results with log transformation incorporated. This doesn't mean that I, recommend using it all the time. You need to make the judgment and to rationalize the decision. So, can you tell me which node has the log transformation technique? Transform variables. Very good. So it would be under modify. And for this case, because you only have 2 interval variables, then you can use a default method. For interval inputs, you can choose to use log or log 10, and with everything else as known and not changed. So, I won't run it for now because, I'll build the regression model and then run it at the same time, so to save some time. So, the first, there are 2 questions in homework. The first regression model that the question asks you to build is the simple linear regression that involves fiber, I think. Right? So, and up till this point, you have both input variables included. And then model, regression model. And this is a simple linear regression. Let me rename the node to make it clear. And here you can customize the specific variables to be included as input. In other words, you can wait. Okay, yeah, I haven't log transformed. I was looking for the log prefix. I didn't see it because I haven't run it, but that's fine. Well, you know what? I think that may matter. So it's better to run it first. Review the results. Logged version of the variables are created. Each of the original variable is the algorithm added an arbitrary 1 to the original variable and take the log. Right. So then let's update the path. Now, I think we will see the updated variables. So now we have two logged version of the inputs. For simple linear regression, I will only keep the fiber. So I will change for the sugar to be no, which is great. Now, simple linear regression would not have these features available to them. Even if you do, it don't make a difference. And given a reasonable correlation between the input and the target, you will find this model to be significant. So up to now, I think you can run it. So review the results. This is a table that you see a lot. This is the mostly the model evaluation, as well as some other diagnostic measures. You have average square error, misclassification rates, standard list of metrics. This output window will be the one I'll focus on. Here, it looks something like the like score ranking chart and things like that, which we'll talk about in the model evaluation chapter. This is plotting the sides of the coefficient. Okay, the regression output sometimes can be very long. If you do a stepwise regression, then there are multiple steps, stacked above each other. And then if you have 10 steps, then you have 10 sections, and maybe more than 10 sections of the output. So sometimes it takes a little trick to get around these outputs. And there is search function here, so you can. So if you know the keyword for the section that you want to look for, then use the search function. So the question here is several key statistics that you're looking for is R squared and adjusted R squared and coefficients, and along with the list of variables. For R squared, you can see that it's 0.3, close to 0.3. No, it's not super good. It's not minimal as well, and which reflects the correlation, the level of correlation between fiber and rating. Right. And then to interpret, the question in the homework asks you to interpret, what does it mean by the coefficient of fiber or log fiber, right? In this case, it's a logged version of fiber. The coefficient is 11.4, close to 11.4. What does it mean? For this simple linear regression case, you would interpret that for each for each unit of increase in logged fiber, the estimated or the average log rating. This time, is it log rating? Did we log transform the target? No. So it's the original rating. The expected or estimated value of rating will increase by 11.4 points. That's if the rating is in the original scale. That looks reasonable, because if I did the log transformation and the scale, the maximum would be at best 5. So the coefficient won't exceed 2 typically. Right? And this intercept indicates that it's way more than 5, the average rating. So rating was not log transformed. So that's the interpretation for the coefficient. Is that clear? Great. We can move on. Next question asks you to build another regression, which is multiple regression that includes additionally sugar. So in this case, you can modify that regression. Then you need to do multiple things, or you can bring in another node, which is another regression model, which I think is easier in this case. I would also rename that regression model just to be clear. And in this case, I won't reject any other variables, so I will keep them as default, and then both input variables will be included. Also, I will not select any stepwise regression models, just because I expect both variables to be significant to contribute to the model, and even if I selected stepwise, neither of the variables will be rejected or will be excluded. But of course you can try, but the results might be the same. And also, just to make a note, here rating is continuous, right? Rating is interval. So for a regression model that works for an interval target, it would be regular regression, linear regression, instead of stepwise regression. But if you take a look at here, this model has already been run. It still is designated as logistic regression. This is, of course, not the case in terms of the actual model that's used by SAS. But SAS was just lazy, I think. SAS didn't change the label, but in fact, it's not logistic regression. It's linear regression. So, you don't really have to care for it. But if you are a perfectionist, you can change it if you prefer, which won't make any other impact. And that's it, and you can run it. So same layout. Now you have three variables, including the intercept. Even though you have only 2 inputs, but you do have an intercept, which is typically the highest in this case, in this homework. Now, first thing to look at is to confirm both variables are included and coefficients are calculated. And you notice that R squared changed quite a bit. Do you recall the R squared before? 0.29 something. Good memory. Close to 0.3, but now it's 0.85, close to 0.85, which is a significant jump. And there isn't too much of a difference between R squared and adjusted R squared, which means that both of the variables contributed meaningfully to the to the regression model, basically. And now, if I ask you to interpret the coefficient of sugar after the transformation, how would you do? Right? For each and every unit of increase in log transformed sugar, and holding everything else unchanged, because now you have two variables, right? The other variable, if there was some change, the coefficient would change for fiber. I mean, there's a fiber, so if fiber changed, then coefficient for sugar would also change. Now, the third part is estimated or average value of rating is expected to drop 13.67 points, right? Anybody recall the coefficient for fiber previously in the simple linear regression? Huh?
I think 11 point something.
11 point something, yeah. So now it changed. It dropped to 9 point something. So that's why the additional clause, the additional statement that says holding everything else unchanged is important here. You know, to be scientific in interpreting the regression results. And if I ask you to write the equation of the regression model after by using these coefficient results, how would you do? In this case, for multiple regression case, you know, you'll write an equation. There's a left-hand side, there's a right-hand side, right? The left-hand side is the target. So, you know, put the name of the target there. Don't simply write target. It's reasonable, right? So whatever is the target here, it's rating. The right-hand side will include the intercept and the additional two terms, which is the coefficient multiplied by whatever the input is that the coefficient is for. Make sense? I think you, out of all the models, you have most experience with the regression, so I don't necessarily need to demonstrate everything. That's it for the leftover about regression. Any other questions? Yeah, simple enough. Okay. Yeah.
So for this, I kind of played around with the homework earlier today. I didn't do a log transform. How would we have known that might have been a good idea, that is good practice?
You can compare the model performances, and if the objective of the project is to have the best predicted model, then, you know, under the cross-validation framework, you can compare two models, one that uses log transformation, the other that didn't use, but make sure that you do the same with the target variable, right? You can't log transform one target, but didn't log transform the other target. You can't compare them because the target is different, right? You know, keeping the same operation on the target but varies the operation on the input, you can see the result, right? Make sense? Yeah. Typically, regression is used to explain the phenomenons. So that's within the explanatory regime of data analysis, and in that regime, people don't care really that much about out-of-sample predictions. In-sample prediction is what they care, because they try to explain everything that is that can be explainable in the training set. So in that case, you won't have cross-validation, but then everything else would be similar. So in the explanatory data analysis regime, then you would simply compare two models on their R-squared. Then you can say, you know, the one model that has the better R-squared is whatever the model that you preferred in terms of log transformation. Yeah. Any other questions? Great. Close that. All right. So neural networks. Yeah. I'm very excited about that. We talked about neural networks. Now let me pause the recording for now. We'll come back if I were to demonstrate some neural networks.